Very good morning to you all. Today we are going to see computer control of processes part 6. First, let us see step response of first order lags in series. This we have seen this as a last part in the previous lecture. It is also a continuous time system. That's why before this we would put one zero order hold. A hold circuit before this we have to put, because it's a continuous time system. So we cannot give digital input directly to this. But anyhow, this will give continuous output. If you want discrete output, you can put a sampler here or a fictitious sampler here. But we cannot give this directly. That's why we need a zero order hold. Zero order hold is required. Its transfer function is 1 minus e power minus ts upon s. This must be preside over this continuous time function. Then we can give this pulse input. M of nt can be given if we include a zero order hold before this. So if you want to find the pulse transfer function means for discrete input, what is the transfer function? So if you want to take pulse transfer function, already we mentioned that this should be presided. So with this given transfer function, this pulse transfer function is cascaded. This pulse transfer function is cascaded with the given transfer function. Now we can give pulse input. That's why it is called HGP of Z, not GP of Z. So if you multiply this in the denominator becomes third order, do partial fraction for this, and you can take this directly. 1 minus e power minus ts can be directly taken out, one sampling period. Therefore 1 minus z power minus 1 can be taken out. Remaining things can be remaining things can be partial fractioned. That is 1 by s. This is the c and c1. C1 is 1 here. C2 is tau 1 upon tau 2 minus tau 1. 1 by s minus 1 by tau 1. Here C3 is minus T2 by tau 2 minus tau 1. So we find the residues here. These are all residues. C2 is one residue, and this is C1, another residue. C0, another residue. So we found the residues for this partial fraction. Now it's ready to find the Z transform by using the formula. So what is 1 by s? 1 by s is step function. That's why we can directly write this here. This is first order function with a equal to 1 by tau 1. That's why we can write this is e power minus at. That's why we can write e power minus a is 1 by tau 1 multiplied by t. A is 1 by tau 1. Here a is 1 by tau 2. That's why we are getting this. So we obtained the pulse transfer function. So what we have to remember, always if it is a continuous function, continuous system, preside over a zero order or first order hold, some hold circuit output, then do partial fraction, then find the Z transform. That is called HGP of Z, or pulse transfer function. Here, n continuous processes are in series. All are continuous functions. G1, G2, G3, etc. Gn are continuous functions. If you want to find the pulse transform of the train of continuous systems characterized by G1, G2, G3, etc., G of Z, you can find like this. But the input that is G1, after cascading, G1 will be in the first system. It should facilitate for discrete input. If it doesn't permit discrete input, then it must be H, G1, G2, G3, etc., Gn. So all can be cascaded here because the output of G1 is continuous. Here, this H converts the discrete input into continuous. That's why all can be cascaded with the H. But here, we are assuming that G1 permits discrete input. That's why it can be written like this. You can multiply and you can directly find. If it doesn't permit discrete input, then it should be multiplied by a whole circuit. Then only one whole circuit is sufficient. But if you find G1 of S, Z transform of G1 of S, you got G1 of Z. Like that, if you find for every function, you will get separately all G of Z. If you multiply all these together, this is not equal to the above one, because each one is separately found the discrete time. The meaning is, if you multiply this way, means each one is permitting discrete input and it gives discrete output. This gives discrete input and discrete output. Each one function permits discrete input, or it takes discrete input and it gives discrete input. That is the meaning. But it's not possible if it is a continuous time system. That's why these two are not equal. So what we have to do is, we have to multiply all these first in time domain, S domain, then we have to find Z transform. Here, one more thing you should remember, that I am finding HGP of Z. How? I am multiplying GP of S by H of S, then I found Z transform for that. I got HGP of Z. Suppose you are having H of Z separately, GP of Z separately, assuming that it accepts discrete input, assuming that it accepts discrete input, you got GP of Z. If you multiply, that is also not equal. So you should remember that if the system has a sampling period between two cascaded systems, then it can be found separately. In other words, each system should accept the discrete input. It is not accepting discrete input, but we are finding GP of Z, and if you put here, means it's wrong. If it permits, suppose GP of Z is a discrete filter, if you have found, then you can cascade. Then also it is wrong, because this gives continuous output. H of Z gives continuous output. If you cascade, again, it's wrong. So this is wrong. You cannot find. You multiply in S domain, then find Z transform. That is very, very important. I think you understand. If a system output is continuous, then it should be cascaded with another continuous system, Finally, you can take sample. A system should preside over this. A discrete system should preside over this. A system that can accept a discrete input should preside over this. But this will take continuous only. That's why if you put H of S, that is hold circuit, it takes a discrete input and gives out continuous out. That is the idea. So it gives continuous to this, it takes discrete. This we should remember. Another interesting thing, yesterday I mentioned that if you take pulse transfer function, without cascading H of S, that is hold circuit, what will happen to the system, that we'll see. I am having continuous system. Having a continuous system. For that, I am giving discrete input. I am giving this is continuous system G of S. G of S. For that, I am giving deliberately. I am giving discrete input. What will be the output? Suppose I am having a car is not started because the self starter is not working. That's why it is not starting. I want to push the car. How I am pushing that? I am pushing, then stopping, pushing, I'm stopping. I'm giving, injecting the pulses. Like that, what will happen to the car? Whether it will continuously move. If you push, it will move immediately, but suddenly it will decrease its speed. Then again, after sampling period, you are again pushing. So if you see the response of that car moving, it will be like this. You are pushing, that's why its speed increases. Then you injected the energy here, that's why its speed whatever the speed you injected as impulse input, suddenly it comes to this velocity. But after that, no energy injection, that's why it decreases. Again, you are giving an injection of that energy, same amount of energy, then it goes up. Why? Earlier it is in 0, that's why it went up to this speed. Now already some speed is there, it is not yet came to 0, that's why you are injecting. Again it goes like this, again it comes like this, again it goes up, again comes like this. It will goes up and down like this. The response will be like this. So if it is a continuous system, for that, if you give a discrete input, its response will be like that. You are pushing the car here, but you give a jerk, impulse input, that's why it moves, but starts decreasing its speed. Again, before it comes to rest, you are giving another impulse, that's why speed goes up, then it comes down, goes up, comes down, goes up, comes down, like that. It will be like this. That's why a continuous system must be presided by a hold circuit H of S, because the hold circuit will take discrete input and gives continuous output, that is given to GFS. Already we have seen that. Uh, uh, the hold circuit, what it will do, zero order hold. If this is the input, means it will maintain the same input till next sampling period. In this sampling period, slightly magnitude increased, it will maintain the same value up to that. Suddenly input is decreased, so it will it is decreased, so it will maintain till next period same value. Like that, you will get a continuous output if you add a zero order hold, or you can include a first order hold. Some hold circuit must be there because it will convert the discrete input into continuous one. All your DAC circuits available in the market are followed by hold circuit. That's why the DAC output is pulses. If you give some number, it will be converted into voltage. Suppose I'm giving 0 to 8 8-bit DAC, in that I'm giving 255 to that, it converts immediately into 5 volt. Its span is 5 volt, let us assume. Then it gives a pulse of 5 volt, that's all. Next sampling period, I'm giving 127. So it gives a pulse of 2.5 volt. So then I am giving some again 255 5 volt pulses. But if you have a zero order hold in that output, what will happen? What I said initially, it gives 5 volt, then 2.5 volt, again 5 volt it is given. So in the output, if you put a zero order hold, what will be happen? It will maintain up to next sampling period 5 volt. It will maintain 2.5 volt next. Then again it will maintain that 5 volt after that. So till it gets next value, it maintains that value. So all DAC circuits available in the market has a hold circuit in the output. That's why we are unknowingly use that as a continuous signal. But some system will give pulse width modulated output, that is different. You should know about that also. If you give continuous pulses as output, the stack will convert this into a continuous signal. Here, this is the system. This is the system for which we are giving pulses as input, because it is a continuous time system. But I am sampling here. If I didn't sample, the dotted line will be the answer. If I sample at the same sampling period at which we are giving input, you will get this as this will be the input. If you see a discrete input, the continuous input will continuously increase its output at sampled values if you join, but it is not the fact. At this point, this amount is injected, but after that, and still next sampling period, it decreases. Then again, at this point, you are injecting something, already it has some energy, you are injecting further, that's why it goes up slightly above. Then again, it starts decreasing till fully it discharges its energy, again you are injecting, so it will be like this. So if it is a continuous time system, you must preside this with a h of s function. Old circuit must be presided by this function. For this presided this system. So then what is this? You notice that suppose this is constant. This is also constant, means what will happen? 1 by 1 minus a z. Then if you find the transfer function, you will get e power minus at, you will get e power minus at, you will get e power minus at. If this is not constant, that way this will happen. How it is not constant? E power minus t by tp. Tp is constant, z power minus 1 is the term here. So this t is not constant. Yeah, this is not. I can tell the other way. This is what this is a discrete system. It won't say what is happening inside. What is happening inside? It will give the values at the sampling instances. It is giving at the sampling instances these values. So if you see, if you join all these values, it is a ramp. Yes, it is e power minus 80. It's correctly giving. But since it is a continuous time system, it is not a discrete time system. If it is discrete, if you inject the input here, it will give this. If you inject here, this will give this. If you inject here, it will give this. Like that, it will continuously give. But it is not a discrete system, it is a continuous system. That's why in between, it oscillates like this. It comes down, go up, comes down, go up, like that. That's why if you see the Z transform of this, it correctly says it is a ramp function, no doubt. But if you see the continuous domain response, it is oscillating like this. I think you understand my point. If you see in terms of Z domain, it is perfectly all right, because it gives e power minus 80, e power minus 80. If you find substitute e power 80, it must be a n t. We have to, if you write in time domain, we have to include that n. So this n is here. That's why for every n, 1, if you put 0, you will get this value. If you put 1, you will get this value. If you put 2, you will get this value. Like that, 2t, 3t, 5t, like that, you will get all these values. Yes, it's correctly giving a ramp response. But internally, what happens to the system? It is decreasing and goes up, decreasing, goes up. That happens inside the system. Its velocity is changing like this. That's why if it is a continuous time system, we must preside by a hold circuit. Now let us analyze discrete time closed loop system. Let us analyze discrete time closed loop system. Discrete time closed loop system. How it looks here, it is a discrete controller. For a discrete controller, input must be discrete. That's why the set point is sampled here, then it is given as input. Here the output is sensed and sampled here, and it is as a sampled. Here it is y of s. Here it is y of s, but here it is y of z. Y of z is given. So it gives a discrete output, d of z. It gives a discrete output, d of z. Controller output is input is e of z and output is d of z. But this sampler is um, is part of this control algorithm. That way we have to think. It gives here, it gives here, it gives d of z, d of z. He mentioned as c of z. Okay. Um, Normally we used to use this c for output. Here he used for controller output. D of z gives, it is a pulse input that should be converted into continuous signal. That's why hold circuit is here. That hold circuit converts that into manipulated variable m of s, continuous signal. That is given to this process. That's all. So disturbance is entering here. We have to think this is system. This is system. So the system is sensed here, and a disturbance is entering here. This is the system. So we should not see this block as separate, mathematically separate, but this all together. Here the disturbance is entering. Here input is entering. Here the input is here disturbance is entering. Here input is entering. The m of s, the input is entering. Here output is coming. These are all part of system. Now let us find. Let us analyze this closed loop system. Here this is discrete system because it takes the discrete input and gives discrete output. But this is a hold circuit. It can take a discrete input and but it will give continuous output. That's why it can be cascaded to. It is cascaded to the system. It's the output again continuous. So we need a sampler to sample, and it is given to the discrete system. A continuous controlled output can be written as this is because of input output. This is because of input. This is because of disturbance. So the total output equal to output due to input m of s and output due to disturbance d of s. This is d of s is responsible for output, and y1 of s is because of this m of s. So you are giving two inputs. One is disturbance, natural, and this is man-made. M of s is man-made. So you're giving two inputs. That's why the output consists of two parts. One is y1 of s and y2 of s. To find z transform of this function, the z transform of y1 of s is hgp of z, c of z. Because to give discrete input, it should be presided by h of s. So hgp of z is the system. Its input is c of z. He wrote like that. I put c of z is the input. That's why it's like this. So this is y1 of z. What is y2 of z? Y2 of z is z transform of gd of s, d of s. Both are continuous. That's why both are multiplied. But we do not know the form of input. That's why the gd of s, d of s is written like this. It is natural input. The disturbance is natural input to the system. Its model is gd of s. That's why we are writing like this. We cannot define pulse transfer function gd of z for the disturbance elements. And we cannot write like this. We cannot write like this. gd of z, d of z we cannot write. But we can multiply these two and we can put z transform of like this. But if you do not know its structure, it's difficult to find. If you know that structure, we can multiply these two and we can find the Z transform. The disturbance is not a sampled signal. So we can write HGP of Z, C of Z, Z transform of GD of S, D of S. So what is E of Z? In that we are going to find the response for that system. We are going to find the response here, closed loop response. We are going to do closed loop response. That's why we have to find error. So what is that? We have the sampled values of Y, that is output. That's why find the difference between Y set point of Z and Y of Z. So multiplied by D of Z. Here you can multiply because between D of Z and the system, there is one sampler. D of Z output is sample. Its sample output is accepted by this as input by this hold circuit. That's why you can multiply D of Z and E of Z. You can multiply D of Z and E of Z. Both are discrete, and here also you can multiply like this because both are discrete. After that, D of Z can be multiplied with HGP of Z. You notice that we found HGP of Z and multiply with the D of Z because D of Z takes discrete input and it gives out discrete output. That's why these two can be multiplied. What is E of Z? E of Z also discrete. You notice here, here it is sampled values of set point we are getting and sampled value of Y of Z we are getting. Therefore, E of Z is sampled value. E of Z is sampled value. That's why that also can be multiplied with this system. We multiply the error, discrete controller, digital controller, and the continuous system presided by H of S. So this is very much possible. We can multiply. Here we have to write like this only. We do not know the structure of D of S, whether it is discrete or continuous. We do not know. That's why we have to write like this. So it's written like this. But for this, it is for input. You can write like this. So if you bring this Y of Z to the left hand side, what you will get Y of Z multiplied by 1 plus HGP of Z D of Z. Then divide on both sides by 1 plus HGP of Z D of Z. You will get this. This is the discrete time closed loop response of a digital control loop. If you know this, you can find the response. If you know Z transform of GDFS, DFS, you can find the response. Otherwise, if you want, if you assume DFS is 0, if you assume DFS equal to 0, then very much possible to find the response of this. If DFS equal to 0, there is no input. That's why this entire part becomes 0. The entire part becomes 0, and you can find this. Otherwise, you must know the DFS, then only we can find the output of this system. You notice that even though we do not know about GDFS, DFS, the characteristic polynomial is this only. About D, what and all in the characteristic polynomial D of Z, HGP of Z. That's all. It is not involved. This is not involved in that characteristic polynomial. That's why the stability of the system is decided by this characteristic polynomial. The common denominator determines the characteristic equation of DDG. The roots of this characteristic polynomial, the roots of this characteristic in a continuous domain. What is the rule? If roots of the characteristic polynomial lies on the left-hand side of S plane, continuous S plane, then left-hand side of S plane, complex plane, then the system is completely stable. Like that, here also we will see what is the rule for stability later. The roots of roots of this characteristic polynomial decides the stability. The roots of characteristic equation determine the stability of the closed loop response of direct digital control. For servo problem, we are assuming that already I said DFS, assume DFS equal to 0 and find the response, servo response. But if you want to find the regulatory response, what you have to do is assume set point change equal to 0, no set point change. These are all equation for changes. Assume set point change equal to 0 and find the response Z transform of GDFS DFS upon 1 plus HGP of Z D of Z. If you find the response inverse Z transform for this, you will get the disturbance response. If you find inverse Z transform for this, you will get servo response. For regulator problem, y set point of Z is 0 and the closed loop response to disturbance changes is characterized by this equation. This already we have seen. If y set point of Z equal to 0, the system response is, it is the disturbance equation. Disturbance changes is characterized by the equation. DFS characterize this system. Then what is mean by Z transform of GDFS DFS? Let y2 of s equal to GD of s DFS. The inverse Laplace transform yields the function in time domain Laplace inverse of GD of s DFS. The Z transform of the sampled value of this function y2 of t yields, we have to find the Z transform of y2 means we have to find the time domain function of this, and then we have to find Z transform. Normally, Z transform will be found from time domain function, but we have the table. If it is in frequency domain, function is available, then what is the Z transform that is available? Doesn't mean that we can find from S domain to Z domain, we can't find. We found for a given time function, we found both S function and Z function. Now we removed this time domain function. We are taking all S functions for the corresponding Z functions. We are lookup table. We are using that as a lookup table. So if you want to find Z transform, the function must be in time domain. That is the meaning. If you want to find the Z transform for this, if you want to find the Z transform for this, what you have to do is you have to find the time domain function. After finding that, how you will get after taking Laplace inverse, you will get, then take Z transform. That is, but we won't write Z transform of Laplace inverse of GD of S DFS. We won't write. Simply we will write Z transform of GD of S D of S, like that. But what is the actual meaning? We have to find a time domain representation for this. For that, we have to find Z transform. Is the Z transform of disturbance effect on the controlled output? What is Z transform of GD of S? Is the Z transform of disturbance effect on the controlled output. Let us consider this direct digital control system. Here, digital controller is there. Then it is its output is given to a hold circuit. This converts a sampler alone is mentioned here. Actually, before this hold circuit, it will be converted into pulses. That is DAC, function of DAC. That is not mentioned here. So DAC, then hold circuit, then final control element, then process. But we didn't mention like that here. So in the simplified circuit, we are giving control output directly to the hold circuit directly give this process variable. Like that we are mentioning, but it is not the fact. The hold circuit output will go to um, um, final control element, that is valve in this case. Let us assume valve. Then its output is going to process. So these three should be multiplied together. Then measuring your system is what? The measuring system takes continuous as input and it gives directly digital output, let us assume. Then this is also continuous measuring. That's why this also should be multiplied, gm of s. So from this sampler to this sampler, all should be multiplied in time, s domain. That is the meaning of this. If you are having a hold circuit, it takes a discrete value input and gives continuous. Its value output is continuous, so it takes continuous output and it gives continuous output. It takes continuous input and gives continuous output. It the measuring system sensor takes continuous input and gives continuous output. Then it is sampled. Or if you combine the sampler with the sensing unit, it takes continuous input and gives out discrete. Therefore, till this all block should be multiplied in S domain. S domain. G of S equal to H of S, G F of S, GP of S, GM of S. You should multiply all together to get G of S. So if you consider such systems, a hold circuit, final control element, process, all are multiplied together. HGP, HFGP. Similarly, in the denominator, HFGP comes. So one more system is in cascade. That's all. But these two are separate because this is separate discrete system. Its output is input output. Both are discrete. That's why it can be separately written. This also can be separately written. But here in the denominator, the GF also comes into picture. No change in the numerator. So HGF GP GM is the pulse transfer function between C of Z and YM of Z. Here you notice that in the forward path, what and all there? In the forward path, D of Z, H of Z, H of S, G F of S, final process, then output. If you put a fictitious sampler here, you will get Y of Z, you will get here. So in the forward path, these are all there. If you find the transfer function from the block diagram, what you will write, numerator is all forward path functions. So H, G, F, G, P, D of Z, that's all. In the denominator, a loop function, 1 plus HGP of Z, whatever in the feedback should be included. Whatever should be in the feedback should be included. Whatever will be in the feedback should be included. What is the, how you will write closed loop transfer function, GC of S equal to forward path transfer function, forward path transfer function upon 1 plus loop transfer function. Here in the loop GM of Z is there. That's why H, G, F, G, P, G, M, D of Z will come into picture. HF, GP, GM of Z is the pulse transfer function between C of Z and YM of Z. So YM of Z by C of Z means there will be a small change in the feedback element. It has sensor, that is GM of Z, that is that comes in the loop transfer function. That you should remember. Closed loop response of a first order process under proportional controller. I am going to use a digital proportional controller to find the response of this system. It has two transfer functions. One is the input output function. Another one is disturbance model, disturbance system. now let us find, this is input output model and this is disturbance model. From that, let us find the response for that. Closed loop response we have to find. Let us find the response. Here, what and all there, you have to see this block diagram. We have a proportional controller here. We have a proportional controller here. A hold circuit we have. These are all processed together. And a disturbance is entering here. And no measurement element that is assumed as 1 in this case. So if you go here, what you will get, here, this is the given system. It is presided by a hold circuit, so we are finding HGP of Z. Before that, on discrete PA controller is there, so these two can be multiplied. Then in the forward path, these two are there. These two are there. What is a proportional controller only is used means d of z equal to kc. That's all. Again, if you write in time domain, m n of t equal to kc e of nt. This is the expression for if you find z transform, m of z controller output equal to kc upon c of z. So output by input, m of z by c of z equal to kc. So this is the transfer function for digital P controller. So what is the forward path transfer function? Forward path transfer function, this HGP of Z and D of Z. So if you multiply these two, you will get this. What is the feedback loop? This forward path transfer function, the feedback element is unity feedback. Therefore, 1 plus the same will come. We have to find the response. Therefore, y of z equal to something multiplied by y z. So this gives the servo response. Servo response this gives. And for disturbance, we have to find. What is disturbance? The disturbance is coming here. What is the response here? We have to see that. Again, the feedback also plays for that disturbance. That's why this loop also should be included. What are the elements in that loop? Forward path is this alone. Forward path is, you see that forward path transfer function. Forward path transfer function is this alone. D of S, GD of S. That's all forward path. So if you see that here, what is there in the forward path? This alone is there. So this is written here, multiplied by D of S. For that we need Z transform, since it is discrete sign system. This is the forward path transfer function. In the feedback path, what is there? You see here in the feedback path, all the elements are here in the feedback path. So this is the forward path. And now this is equal to 0. This is equal to 0. This is equal to y set point equal to 0. That's why this is not here. While seeing disturbance alone. So this is the forward path. Remember the block diagram reduction. This is the forward path. This is the loop that it has. Therefore, this is equal to 1 already I said. This is equal to 1. This is final control element also equal to 1. This is given. This is given. This is given. This is KC. And the hold circuit is 1 minus z power minus 1 by s, or 1 minus e power minus ts by s. This is also given. So you will get this is 1. This is also equal to 1. So you will get the closed loop response for this disturbance is like this. So you should understand that why we wrote for disturbance closed loop response is like this, because there is one forward path and closed loop feedback path also there. That's why this comes into picture. This already we have seen this in derivation also, but pictorially if you see, we can easily remember why this term comes here. Because if you use that block diagram reduction, easily you will get this. So where H, GF, GP, GM is the pulse transfer function between C of Z and Y M of Z. This M comes into picture here. We are seeing this, Mm, now this is the forward path function of disturbance. In the denominator, the closed loop path is written here. Now, how to find the response? By assuming d of s equal to 0, we have to find the response for this part. Then, if it is not equal to 0, we have to assume this equal to 0, and we have to find the response. After that, we can add these two together if it is not linear. It's linear, then we can add. Mathematically, this is linear. So we can add these two responses. First, let us find this by assuming d of s equal to 0. The closed loop response of first order system under proportional controller. Initially, we are going to find servo response. That's why we are assuming that d of s equal to 0. Then y is it obvious? The first part alone will come. First part alone will come. That is kp kc 1 minus e power st e power e power t by tau that is assumed as b, that is assumed as b e power minus tau sampling period by the time constant of the system, tp, time constant of the system. So here you notice that e power minus t by tp, you are getting, here. If you assume that equal to b, you will get a simplified expression. Simplified expression like this: b is equal to e power minus t by tp. Tp is the time constant of the process. Now let us find the response for step input. That's why substitute y set point of z equal to step input 1 by 1 minus z power minus 1. If you substitute here, now we have to find. Now we have to do that partial fraction and separate this into separate functions. After doing the partial fraction, you will get this as the response. This as the response. This as the yes. This is the response. kpkc 1 plus kpkc 1 minus e power y n of t equal e power. This is e power minus nt upon tp. So we got this response for servo. What is the steady state value? To find steady state value for this, we didn't do z inverse for this. We have to find yourself z inverse for this. If you find z inverse for this is the answer. Already we have seen how to find z inverse for given function. So what is the final value of this response? Multiply 1 minus z power minus 1 with this, and let z tends to 1, you will get. So if you put 1 minus z power minus 1, if you multiply with that and let z tends to 1, you will get this. You will get this. So therefore, steady state value is this. Then what is the offset? 1 minus this. This is the steady state value. Let us assume that it is 0.8. So yeah, step input is 1. 1 minus 0.8 equal to, this is equal to 0.2. 1 by something. Definitely is less than 1. So it is 0.2, let us assume. So this is equal to, this is equal to 0.8. If you want to find the regulatory response, you have to assume set point equal to 0. If you want both responses, add these two together. That's all. That y of z equal to, this is what d of s equal to 1 by s. You multiply that d of s with that system. With that system, what is this? With this, you multiply 1 by s step disturbance. Then do partial fraction and find z transform. You will get this. You will get this. This you got forward path. This is feedback path. Now, if you find z inverse for this, you will get y of nt. You will get y of nt. And this also left for homework. You can find y of nt yourself. The transfer function of first order process with the dead time. Suppose the system has a dead time, then what is then what is the response, closed loop response of first order plus dead time? This first order, it has some dead time here, it has some dead time here, it has some dead time here. Dead time is tau d. The tau d can be written as integral multiple of sampling period. Integral multiple of sampling, k times sampling period, directly it is giving. So suppose the dead time is 5 seconds, the sampling period is 1 second. So it is 5. Tau d equal to 5 means k equal to 5. K equal to 5. K equal to what? K equal to tau d total dead time divided by t. If it is integer, then no problem. Very simple. So k is an integer in this case. HGP of z, we have to multiply this by, yes, hold set code 1 minus e power minus ts upon s, kp e power minus kts upon tau s plus 1. You are writing. Now this dead time kt equal to td becomes kt here. Notice that td becomes kt, k sampling period. So if you find z transform for this, directly you will get z power minus k. That can be taken outside. Yes, it is taken outside. Remaining things are here. 1 minus e power minus ts upon s, kp tau s plus 1. This also can be taken outside. 1 minus z power minus 1 also can be taken outside. For the remaining thing, and if you found that z transform, you will get this. You will get this. So this is the closed loop response of first order plus dead time process. First order plus dead time process. How to find z transform for this? Z power minus k. Then for this part you can write 1 minus z power minus 1. For this part, what are the remaining parts? Z transform of kp. Kp also can be taken outside. Kp also taken outside. 1 by s multiplied by tps plus 1. tps plus 1. For this you have to find. Or you can write, take this tp also outside. You will get TP also you will get outside, and here you have to write 1 by TP here. So for that, if you find Z transform, finally you will get this. Finally, you will get this. What's time now? If that time is integral multiple of that time, then you can take Z power minus K outside. Otherwise, you have to go for modified Z transform. You have to go for modified Z transform. If it is not integral multiple of, if it is not, that time is not integral multiple of sampling period, then you have to go for modified Z transform. Otherwise, you can simply find like this. Otherwise, you can find simply like this. Any doubt?